The distribution of pulmonary blood flow is a function of gravity, cardiac output, and pulmonary vascular resistance, or PVR. Because blood is a relatively heavy substance, it is gravity dependent. Blood will naturally move to the portions of the body, or portions of an organ, that is closest to the ground. Blood flow normally moves into the gravity-dependent areas of the lungs. So given this, body positioning will certainly affect the distribution of the pulmonary blood flow as well, whether you're standing up or lying down. From the base to the apex, the lung exerts roughly 30 centimeters of water pressure. So when blood enters about midway through the lung, it will take about 15 centimeters of water pressure to get the blood to the apex or the top to overcome the gravitational force. Second factor I mentioned was cardiac output. By definition, cardiac output is the total volume of blood discharged from the ventricles per minute. It can be calculated by simply multiplying the stroke volume by the heart rate per minute. Even though total blood volume varies with age, body size, and the sex of an individual, the normal adult carries about 5 liters of blood. Of this volume, 10% will be in the pulmonary circulation. The cardiac output is a driving force for the pulmonary arterial pressure. It helps to overcome the alveolar pressure and drive blood to the apex of the lungs, or the top. Lastly, we have pulmonary vascular resistance, or PVR. Vascular resistance, by definition, is the resistance that must be overcome to push blood through the circulatory system and create flow. In the pulmonary system, there are several known mechanisms that change the vascular resistance. These can be classified as either active or passive mechanisms. Active mechanisms that affect vascular resistance include abnormal blood gases, ABGs, pharmacologic stimulation, and pathologic conditions that have a direct effect on the vascular system. Passive mechanisms refer to a secondary change in pulmonary vascular resistance that occurs in the response to another mechanical change. So if a mechanical change factor in the respiratory system changes, a passive increase or decrease in the caliber of the pulmonary blood flow or blood vessels also occurs. The normal pulmonary vascular resistance is 0.25 to 1.6 millimeters per mercury minute per liter. It can be calculated by simply taking 80 and multiplying that by the difference of the mean pulmonary arterial pressure from the mean pulmonary artery wedge pressure, and then dividing that by the cardiac output. So there are 3 primary factors that determine the resistance to blood flow within a single vessel. There's the vessel diameter, or the radius, vessel length, and the viscosity of the blood. Of these 3 factors, the most important being the diameter. The reason for this is that the vessel diameter changes because of contractions and the relaxation of the vessel's smooth muscle in the wall of the blood vessel. So very small changes in vessel diameter lead to large changes in resistance. Vessel length does not change significantly, and blood viscosity normally stays within a small range. So according to Poiseuille's law, he states that the velocity of a liquid flowing through a capillary is directly proportional to the pressure of the liquid and the 4th power of the radius of the capillary, and inversely proportional to the viscosity of the liquid and the length of the capillary. In terms of flow will decrease in response to decreased pressure and tube radius, and flow will increase in response to decreased tube length and fluid viscosity. Conversely, flow will increase in response to an increased pressure and tube radius, and decrease in response to an increased tube length and fluid viscosity. Assuming the pressure remains constant, decreasing the radius of a tube by 1/2 reduces the gas flow to a 1/16 of its original flow. So next I want to show a drawing that I had come up with to show a better illustration of the distribution of the pulmonary blood flow in each zone of the lung. So as you can see in the drawing that I made, I'm certainly no artiste, but as you can see along the top in zone 1 from left to right, it is the least gravity dependent area. The alveolar pressure is sometimes greater than both the arterial and the venous intraluminal pressures. As a result, the pulmonary capillaries can be compressed and the blood is prevented from flowing through the region, as you can see in the third area on the top right corner. Under normal circumstances, this situation does not occur because the pulmonary arterial pressure generated by the cardiac output is usually sufficient to raise the blood to stop to the top of the lungs and overcome the alveolar pressure. When the alveoli are ventilated but not perfused, no gas exchange can occur and alveolar dead space exists. So in the second area in zone 2, in the middle from left to right, you can see that it's defined as those areas of the lung where the pulmonary arterial pressures exceeds that of alveolar pressure. However, alveolar pressures exceed those of pulmonary venous pressures. When the alveolar pressure is larger than the pressure in the pulmonary veins, the relevant pressure gradient determining the rate of blood flow is that between the arterial and alveolar pressures and not between the arterial and venous pressures. This arises because the alveoli begin to compress the pulmonary capillaries, and thus the alveolar pressure becomes a more limiting factor to the blood flow than the pressure within the pulmonary veins. So zone 2 usually includes the top and middle portions of the lungs in a healthy upright individual at rest. So as you can see, you have the compression at the top right corner, and then as you go further down on the column, the pressure starts to build up, which therefore has greater blood flow and perfusion. So in zone 3, it is the most gravity-dependent area. Both the arterial and the venous pressures are greater than the alveolar pressure, and therefore blood flow through this region is constant. Because the arterial pressure and the venous pressure both increase equally downward in zone 3, so from the top in each column down, the pressures, like I said, begin to increase. So the arterial venous pressure difference, and therefore, so because the arterial pressure and the venous pressure both increase equally downward in zone 3, the arterial venous pressure difference and therefore blood flow is essentially the same throughout all 3 zones.